We speak about heating probabilities for nonlinear systems of stochastic waves.
So thank you. Let me begin by thanking the organizers for the invitation and giving me the opportunity to speak and present these results at this meeting. So I'm speaking on hitting probabilities for nonlinear systems of stochastic waves. This is joint work with Marta Sant-Solé from University of Barcelona. And this is sort of the completion of work that was done in large part during the semester program here at the Newton Institute, where Marta and I shared an office and couldn't avoid working together. This is part of a general type of problem that I've been working on for a number of years. So some of you may have heard me talk about this general type of question before, though not specifically for systems of wave equations. So I'm going to give an introduction to the problem, but maybe not as detailed as I've given in previous talks. I do want to mention some benchmark results on the Gaussian case. So we're mainly interested in solutions of nonlinear systems of stochastic PDEs, but of course it's important to know the results for the linear equations, and in which case the solution is Gaussian. And this sort of tells you what to aim for when you're studying the nonlinear equations. And so in particular, I'll present our results for the systems of stochastic wave equations and compare them with results that we've obtained that have been obtained in other papers for systems of heat equations. And the results are not quite as good for the wave equation as for the heat equation, so I'll explain why the results are different. And I want to mention that a preliminary version of the results was presented here by Marta in July 2010, so just at the end of the semester program. The work was preliminary. She mentioned that. In the meantime, in the last 2 years, we worked hard to solve all the details that remained. We had done a large part of the work then. The results have evolved. So evolved does not necessarily mean improved, because you think you've proved certain things, and then you work out the details, and you realize you've proved something slightly different, not necessarily better. Okay. So what is the basic problem that we're interested in? So we're going to be considering a process, a family of random variables u of x. So x is a parameter. This is in Rk, k-dimensional. But for each x, u of x is a random variable with values in Rd. Okay, so Rd valued, and the parameter is in Rk. It's a continuous stochastic process. We fix a subset of the parameter space, compact with positive Lebesgue measure, and we're interested in the set of positions in Rd visited by this process when the parameter ranges over the subset I of the parameter set. So we look at the set of positions in Rd visited by the process as x ranges over this subset I of the parameter space. And we'd like to get bound, so for a given set in the range space, we'd like to bound the probability that the process visits that set. So the range intersected with A is non-empty, means the process has visited that set. We'd like to estimate this probability. In particular, we'd like to know which sets are polar. So which sets are visited with probability 0, so are not visited. Which sets are visited with positive probability, so which sets are nonpolar. And this is sort of the basic question that we're interested in. Once you've answered that, you can address a certain number of other questions, like figure out the Hausdorff dimension of the range or the Hausdorff dimension of level sets. These are sort of subsidiary questions. And in principle, once you've answered this type of question or gotten upper and lower bounds on these hitting probabilities, you can answer several other questions. I'm not going to discuss that. What is the first example of a result on hitting probabilities that I want to mention? So this is the result that got us started on this project to begin with. And so this concerns the Brownian sheet. So here the process is indexed by the non-negative orthant in Rk. It's a centered continuous Gaussian process, so it's defined by its covariance that is written here. The coordinates are independent, so for different I and j, I have independent variables. And for I equals j, I have this covariance between bi of x and, say, bi of y if I is equal to j, just the product of the minimum of the various coordinates of x. So x has k coordinates, y has k coordinates. If k is 1, this is simply Brownian motion. And so this is a result obtained by Devarkosh, Nevizan, and Zanchi in 1999. So in the case where the I, so the subset of the parameter set, is a product of intervals, so say a rectangle in some sense, they have obtained this upper and lower bound on the probability that the Brownian sheet visits the set A when the parameter varies in this rectangle I. Okay? So here we have an upper bound in terms of Newtonian capacity. So I'll mention what that is on the next slide, but I'll give a definition. There's a number of things to observe here. First of all, you have the same quantity on the right and the left, except for the constant. So up to a constant, you sort of have the best possible inequality. And the dimension here in the capacity is identified, d minus 2k. So d, the value space, rd valued, and k, the parameter space. And it's also maybe interesting to point out that this is not, it's a local result in the set that A has to be not too far away from the origin. So say ball centered at 0 of radius m. It's not a large deviation result. For example, if you translated A off to infinity, you could not get a lower bound of this kind because simply in this compact region of the parameter space, it would be very unlikely that the sheet would go so far away from the origin. So this is not a large deviation result. It's a result locally in the value space, and it's sort of measuring this hitting probability in terms of the size of the set A. So this capacity is going to mention how big the set is in some sense. So big sets will be hit with positive probability, and small sets would be hit with maybe 0 probability, but these sets are not very far from the origin. And were also related results of Hirsch and Song for the Ornstein-Uhlenbeck sheet instead of the Brownian sheet. So yeah, this is just recalling the notion of capacity or Newtonian capacity. So if you've never seen this, it's kind of a little bit involved, but you obtain the capacity by first computing this notion of energy. So you take probability measures supported on the set A, and you have these kernels k beta, which are different according to the value of beta. If beta is between 0 and d, it's this modulus to the power minus beta. Beta equals 0 is a logarithm, and beta negative is 1. And so you take a measure supported in A, and you compute this double integral, and that gives you something called the energy. And then you look for the measure which minimizes the energy and take 1 over that and gives you the capacity. Okay, so it's not so clear the first time you see this, but it's interesting to look at the case where A consists of a single point. So A is just a singleton. And then you see that if beta is negative, for example, so there's only one probability measure that has its support on a singleton. And you're integrating the kernel 1. So you get 1. 1 over 1 is 1. So you get this 1 if beta is negative. If beta is positive, again, you have a single probability measure with support on this singleton. K beta, when beta is positive or 0, is infinity at the origin. So you have one position, and the position minus itself is 0, so you're integrating infinity. Gives you infinity. 1 over infinity is 0. Okay, so it's just nice to remember that the beta capacity of a singleton is 0 if beta is non-negative. And then you can check things like if A is a subspace of Rd with dimension L, then the beta capacity is positive for beta less than L and 0 for beta bigger than L. So that's sort of a first result for the Brownian sheet, which is very sharp and precise. And then the next result concerning other Gaussian processes, which with somewhat less structure, but still some structure, is this idea of anisotropic Gaussian random fields. And so here we consider a centered Gaussian random field. Again, its values are in Rd. The components are IID. And so you need the covariance, or what's essentially equivalent, the L2 norm of increments. Again, if you consider a rectangle, you need some conditions on this Gaussian field. So one condition is simply that the variance is bounded above and below. And the other condition concerns this L2 norm of increments, or sort of the expected square of increments. And so here you see that we have these numbers h1 to hk that appear in these exponents. So if you fix all the coordinates except coordinate j, hj is simply the Holder exponent as you look at the process with that particular coordinate varying. And you have a different Holder exponent for each coordinate, which is why it's called anisotropic. Okay, so this is sort of the main condition, and sometimes there's this additional condition that this conditional variance is bounded below. Again, here you have the same expression as the one that appears above, the increments to the power hj, and hj can be different for each j. Okay, so here's a type of Gaussian random field, and for this type of Gaussian field, there's a result proved by Yimin Xiao and several co-authors, which says the following. So again, there's a upper and lower bound on the hitting probability. So the probability that the process visits the set A when the parameter range is over the parameter set I is bounded above and below. So here you notice, first of all, that on the right I don't have capacity anymore. So I have Hausdorff measure. And I'll remind you what that is for those who are not so familiar. But a good thing is there's the same dimension. So there's the same dimension on the left as on the right. The value space dimension little d appears here. And then the quantity q is related to the Holder exponents that were coming from the previous slide. So the Holder exponent in each, as you vary each coordinate. Okay? So you take 1 over the Holder exponents, add them up, and that gives you the dimensions that appear on the left and on the right. We had obtained a special result of this kind. And this is sort of, a general result. It's much less specific than the Brownian sheet, much more general class of processes. It tells us sort of what sort of inequality to aim for a non-Gaussian process. And in particular, we like to summarize everything in the Holder exponents, so in the dimension of the value space and the Holder exponents as they appear here. But it's slightly less good than the result of Khoshnevi-Zan and Shi in the sense that there's Hausdorff measure here and not capacity. Okay, so Hausdorff measure, as you recall, how do I obtain the beta-dimensional Hausdorff measure of a set A? Well, I cover the set A by balls of small radius. I take the diameter of the power beta, add all this up, optimize over the covering, and take the limit as this epsilon, the small radii go to 0. So that's for beta positive. For beta negative, we just define h beta of A to be infinite. Okay, so this is another measure of the size of the set, sort of like capacity was a measure of the size of the set. The two quantities are related, and in particular, there's these inequalities here. If the beta 1 capacity is positive, the beta 1 Hausdorff measure is positive. But the beta 1 Hausdorff measure positive only implies the beta 2 capacity is positive for beta 2 smaller than beta 1. So the two quantities are related but not identical. Again, it's interesting to look at the case where A consists of a single point and see where the difference is with regard to capacity. So for beta negative, by definition, we put the Hausdorff measure to be infinity. If beta is 0, so if we take a single point, we only need one ball to cover that point. With small radius, take the radius to the power 0 gives 1. And there's no sum because you only have one ball, so you're getting 1. Sort of, you can't do better than 1, so you have this 1 here. If beta is strictly positive, you cover your singleton by a ball. So maybe of radius epsilon. You raise epsilon to the power beta. As epsilon goes to 0, this would go to 0. Okay? So the only difference with regard to capacity, at least with what I'm showing here, is the case beta equals 0. Remember, the capacity of dimension 0 of a singleton was 0, and here it's 1. So if on the right-hand side I have a bound in terms of Hausdorff measure, it's doing slightly less well than if I had a bound in terms of capacity. Okay, yeah, so this is a comment here. The zero-dimensional capacity of a singleton is 0. The zero-dimensional Hausdorff measure of a singleton is 1. So having Hausdorff measure on the right is a slightly less good bound than having capacity on the right. Okay, so we're interested in nonlinear systems of stochastic wave equations. So let me take the wave operator. Okay, this is a bad start. So second derivative in time minus Laplacian. Yes, so second derivative in time minus Laplacian. Very good. But anyway, I have a system now of wave equations. And so on the right, I have additive nonlinearities and multiplicative nonlinearities. The equations are coupled in the sense that these functions b1 to bd depend on all of the components. So each equation, the right-hand side uses up all the components. So do the multiplicative nonlinearities. T is time. X is in our k. K, the spatial dimension here will be 1, 2, or 3. So we were mainly interested in spatial dimension 3, and that's where we did most of the work is maybe the hardest, but we also covered cases 1 and 2. Higher dimensions are different and are not covered. I'm taking the nonlinear function simply to be Lipschitz, because we're not really aiming for the difficulties are elsewhere versus assuming, say, locally Lipschitz, so I'm taking them globally Lipschitz. There's initial conditions, which are the initial position and initial velocity, since in principle I have a second order in time here. And then the W dot J's are Gaussian noises, so I'm going to say what that is in a second. But I just want to mention that this work is related to other projects that were developed also over the years. And so the first case was the case that came out of Eulalia Nieuwelart's PhD thesis. So this was the wave equation in spatial dimension 1. So here we have the second derivative in time. And it was considered in reduced form, but essentially equivalent to this. And W dot was simply space-time white noise. We also considered with Eulalia and Devar-Koshnevisan the heat equation in spatial dimension 1. So systems of heat equations, again with space-time white noise, and the heat equation in higher spatial dimensions. So this is a project that is essentially complete. Here, first derivative in time minus Laplacian. In higher spatial dimensions, of course, we have to take spatially correlated noise. So here, white in time and spatially homogeneous. And we've sort of taken noises with this particular correlation function, so x minus y to the power minus beta, so a Riesz kernel. And we'll also be doing that for the wave equation. Yeah, the driving noise, as I said, was in spatial dimension 1. Usually you take space-time white noise, so independent components. It's d-dimensional noise, independent components, but space-time in t and x. And then in higher dimensions, which could also include dimension 1, which do also include dimension 1, we take spatially homogeneous noise that's white in time. So the covariance is given here. Again, independent components, white in time, so this Dirac delta function, and then this covariance in the spatial variables. Beta has to be between 0 and k, and norm is the Euclidean norm. So we want to discuss hitting probabilities, but of course, if you sort of get up in the morning and say, I want to discuss hitting probabilities for such and such an equation, like the Kahn-Hilliard equation that Annie Millet mentioned, well, you have to do a fair amount of preliminary work. And for the heat and the wave equation, a lot of that work was already available. And so let me just mention what you need sort of to start working on hitting probabilities. Of course, you need existence and uniqueness of a random field solution. So for every t and x, you need a random variable u of tx that solves the equation. For the heat or wave equation in dimension 1. This is a very old problem, beginning with Walsh, and many people here, dozens of people have worked on this. I just want to mention that in the case of spatially homogeneous noise with the Riesz kernel with exponent beta, this condition beta between 0 and 2, minimum k, say if k were 1, is necessary and sufficient for existence and uniqueness. Then the key ingredient you need, here I'm first going to discuss upper bounds, and then in a few minutes lower bounds, is moments of increments. So for example, when you want to prove Hölder continuity, you have the Kolmogorov continuity theorem. You study moments of increment, so the LP moment, say of usy minus utx at different space-time positions. And typically you get some quantity here which depends on sy, t, and x, which usually, sort of like in the anisotropic Gaussian fields, is t minus s to a power plus x minus y, possibly to a different power. So for example, in the heat equation, these exponents are different. The spatial behavior is different from the behavior in time. Heat equation h1 is a quarter, h2 is a half. For example, in the one-dimensional wave equation, h1 is equal to h2, and both are equal to a half. Yeah, so if you have this type of information, you're in business. So for the heat equation in higher spatial dimensions, you have this sort of inequality. So with the Rees kernel with exponent beta, for h1 less than 2 minus beta over 4, and h2 less than 2 minus beta over 2. So at least in the literature, it's not explicitly written that you have equality here. In terms of Holder continuity, it doesn't really matter, and in terms of our results, it doesn't matter either. For the wave equation in dimensions 1, 2, and 3, this sort of inequality is a rather difficult inequality. So Marta, Sanz, and I, in the Memoirs of AMS, established this, again, for h1 equals h2, strictly smaller than 2 minus beta over 2. You cannot do better. So you want optimal exponents as far as possible. Okay, so if you have existence, uniqueness, and moments of increments, these are two important ingredients. And the third ingredient is existence of a uniformly bounded density. So u of tx should have a probability density function, which should be uniformly bounded. To get this, you need additional smoothness hypotheses on B and sigma, because you're typically going to use Malevin calculus type arguments. But if you have these three properties, then we've sort of worked out that you get directly from this an upper bound on hitting probabilities in terms of Hausdorff measure, sort of similar to the result of Yimin-Xiao that I was mentioning before. Okay, so with these properties, so having a bound on moments of increments of this kind with certain exponents here in the time and spatial increments gives you a bound. Yeah, so in general, moments of increments plus uniformly bounded density gives you an upper bound of this kind. The probability that your process visits the set A, take I and j to be rectangles, so I is an interval of time, j is a rectangle in the k-dimensional space, is bounded above by Hausdorff measure of A, and then the dimension that appears. So there's the dimension D that appeared in all the previous cases. This is the dimension of the value space. Q is the inverses of the Holder exponents. So I have time variable is a one-dimensional variable, so 1 over h1. And then the spatial variable has k parameters. But in the anisotropic result of Yimin-Xiao, you had to add up the exponent, inverse of the exponent for each real valued parameter. So if we have a k-dimensional spatial variable, we have to add up 1 over h2 k times. So this is the quantity that corresponds to what you would have in the result of Yimin-Xiao. So d minus q is good, and it's then not quite as good because we're in a non-Gaussian situation, so we have to subtract eta. For any positive eta, you have this inequality. Of course, the constant depends on eta, and we don't have this inequality for eta equals 0. And from this, you can deduce if points are polar, that points are polar in high dimensions. So if d is bigger than q, q being given by this quantity, you know that points are polar. Of course, the h1 and h2 are different depending on whether you're looking at the heat equation or the wave equation and in which spatial dimension. But sort of generically, you have a similar result for the 4 equations that I've mentioned. So this concerns upper bounds. And then for lower bounds, what are the ingredients that you need to study to get lower bounds on hitting probabilities? So you need positivity of the density. So the probability density function of UTX should be strictly positive. Maybe you can even sometimes get it bounded below by a Gaussian density or something like that. For the wave equation here, there's a result of Eulalia-Nieuwelaert that does this. But the other thing you need is an upper bound on the density of this random vector. So given s and y, u of sy is an rd valued vector. This is another rd valued vector. So we have an r2d valued vector. I'm calling this the 2-point density, so taken from 2 space-time points or positions. And so the probability density function of this r2d valued random vector should be bounded above by an expression that I've written here. And we're going to look at this expression a little bit more closely. It would look a little bit more familiar if here I put exponential and then 1 over this fraction, so z1 minus z2 square over delta square. Then it would sort of look like a Gaussian density. I would have the increment squared and then a variance and a term in front of the exponential. So this would sort of look like a Gaussian density. And if you have that, that's better, but for our purposes, this is sufficient and sometimes easier to prove. Okay. Then there's this factor in front of the exponential if you had this bracket replaced by an exponential. So this bracket here, there's a certain exponent. So remember, delta was the quantity I was getting from estimating moments of increments. There's going to be a power here. And you'd like this power to be as small as possible. So the best you can hope for is gamma equals d, so the dimension of the value space. And this is what you would have for the linear system of equations, so b 0 and sigma constant. So if you can get gamma equals d, you're very happy. If you can get gamma close to d, maybe you're already fairly satisfied. If you have these two properties, so positivity of the density and this upper bound on the 2-point density, then you get a lower bound on the hitting probability. So the probability that the process visits the set A is bounded below by a constant times the capacity of A. Again, the dimension that appears here, so on the one hand, there's gamma, which is the exponent that was up here. And the best possible would be d, which is what was, for example, the case in the Koshnevi-Zan and Shi result. And q, again, is the appropriate term, sum of the inverses of the Holder exponents. So 1 over h1, and we have a k-dimensional spatial variable times 1 over h2. Okay, so you can, directly from these two properties, you get this lower bound, and you have the best possible result if you were able to prove this inequality up here with gamma equal to d. And again, this would tell you that points are not polar in small dimensions, for example. So when gamma is less than q, you would have that points are not polar. Okay, so the main part of our work, in some sense, was to get this kind of inequality. And then there's sort of a general argument that leads you to this result here. And the question is, for which gamma can we prove an inequality of this kind? Okay, so I want to say a little bit about the results that exist in the 4 cases that I've mentioned, and then show where the difficulties are in some sense. Yeah, so the first case was the wave equation in spatial dimension 1, and then in that case we have the optimal result, so gamma equals d. h1 and h2 are 1/2, so we have that the hitting probability is bounded below by the d minus 4 dimensional capacity of A. So this is sort of the best possible result that you can obtain. For the systems of heat equation in spatial dimension 1, so here with space-time white noise, here we get almost the best possible result. So gamma can be as close to d as you want, but not quite equal to d. The Holder exponents are 1/4 as I said, and so sum of the inverses, 4 plus 2, 6, that's this 6 that appears here, and so the gamma is d plus eta is appearing there. So this, again, is a rather satisfactory result because we almost have the optimal dimension here. For systems of heat equation in spatial dimension 1, again, we almost get the optimal value of gamma and the Holder exponents that I've written here. And so we have, again, the almost optimal lower bound on hitting probabilities, not optimal because of this extra bit eta here, but eta can be as small as you want. Of course, the constant then depends on eta. And then for the wave equation, yeah, so here is where a slight difference appeared that we had not completely anticipated. So d plus eta would be as good as we had above, but then there's this extra blue term. And we hadn't quite accurately identified that term back in 2010. Slightly optimistic. But that gives this bound here. So d plus eta. So the difference between wave and heat is there's a 4 up here and a 2 down here. Otherwise, it's the same. And then this extra term that we would hopefully like to avoid, but for the moment it's there. Okay, so we can sort of expect that it should not be there, but that's what our method gives. And I want to spend some time explaining sort of how we get this type of result and where this term is coming from. And as I said, the main effort in the calculation is to determine to obtain an inequality of this type. So have the 2-point density bounded above by this quantity delta, which measures the size of increments, moments of increments. So to get the appropriate power here and the quantities there. So how do you get an inequality of this kind? So here's where we're going to use Malliavin calculus. So Malliavin calculus gives you an explicit formula for the joint density of any random vector. So say it's R2D valued, let me call it Z. Malliavin calculus gives you a formula, and you can manipulate that formula to get the following bound that I've written here. So the density of this random vector, and it's R2D valued, so I have D components in Z1 and the remaining D components in Z2, is bounded from above by an expression of this kind. And so, this expression might seem a little bit mysterious. There's the two factors. The one on the right is kind of familiar. It sort of looks like the probability distribution function, or 1 minus that, in some sense, of each component. So that's not so complicated in some sense. This factor is a more complicated factor, which involves iterated score code integrals of inverse of the Malliavin matrix and certain Malliavin derivatives of Z. Okay, so I'm not assuming that everybody is familiar with Malliavin calculus, though probably most people are. But I'll say a little bit about this in a minute. We're going to apply this bound to a particular random vector. So this was for any Z in some sense. So I want the 2-point density. So I want the density of USY, which has D components, 1 to D, and UTX, which has D other components, U1 to UD. And it's slightly simpler to subtract the first D components from the last D components. It's sort of equivalent to have the density of this vector or to have the 2-point density where you do not subtract these extra terms, since one is just a very simple function of the other. So this factor here is the one that leads to the factor in front of the exponential, or in front of this bracket. Whereas these probabilities lead to the other factor. It's easy to see why these probabilities can lead to a factor of this type. You simply apply Chebyshev's inequality. Okay, so you divide by this, and you have a moment of an increment, and that gives you this expression. And then, as I said, getting the exponent gamma is the hard part. So the hard part is to understand how this term here leads to this expression there. And that's what I want to explain a little bit. So, yeah, this is what we want to do. We want to explain how this object leads to this quantity here. And so there's an explicit formula, as I said, for this quantity, which is an iteration of score code integrals and inverses of Malliavin matrices and Malliavin derivatives. And the first time you look at this, you say, it doesn't really make much sense. I can't really understand. There's too many symbols. What do I do with this? But it would sort of be nicer if there weren't these score code integrals. So let's just remove them for a minute. And then suddenly the line looks simpler, right? There's fewer symbols. And you're able to figure out what's going on. So gamma Z is a matrix. So I'll say a little bit about what this matrix is. Its inverse is a matrix. DZ is a vector, so I'm multiplying a matrix by a vector. And here I'm taking the component number 2D, so the last component. So I'm just taking the last row of the matrix times this vector. And here I'm taking the next to the last row of the matrix times the vector. And here the first row of the matrix times the vector. So I'm running through the rows of the matrices from last to first and multiplying each row of the matrix by this fixed vector. Okay? A fixed column vector. So that looks good. And in some sense, we took away these score code integrals, which are, maybe complicated to compute, but it's not so bad because at the price of an inequality, you can remove them, actually. And so I'm not being too precise in which norms I put here, sort of Sobolev norms, but at the price of putting in norms, and since we're looking for a bound, this is sufficient, I don't really need to worry too much about the score code integrals. They're not present anymore. Okay, so I want to look now more closely at the Malliavin matrix and the vector of Malliavin derivatives. So this is our 2D valued object I'm looking at. So I have the first D components, which are the solution at position Sy, and the last D components, which are the difference of the solution at position Tx and position Xy. And so the Malliavin derivative of Z is just this column vector, in which I take in each coordinate the Malliavin derivative of the corresponding coordinate of Z. And if you look at this, you immediately see that there's a big difference in the first D coordinates and the last D coordinates. The last D have increments. And if Tx is close to Sy, these increments are going to be small. And the order of magnitude is about delta, so the quantity that was measuring the size of increments. Whereas the first D coordinates, there's no increment, so I just have a fixed random variable. So these are essentially of order 1. So I have D coordinates of order 1 and then D coordinates of order delta. And so these two different orders are going to play a significant role. Now let's look at the Malliavin matrix. So again, I have the same vector I had before with 2D components. And so the Malliavin matrix is like the variance-covariance matrix. I take inner products of Malliavin derivatives. I'm not going to say what those are, but I just take each coordinate inner product with every other coordinate. So there's 4 blocks, right? Because Z has 2 blocks. So there's the upper left block where I'm taking, there are no increments. In the 2 corner blocks, lower left and upper right, there's increments in one coordinate but not in the other. And in the bottom right block, there's increments in both entries. So you expect that gamma 4 is smaller than the gamma 2 or gamma 3, and gamma 1 is roughly of order 1. So the order of magnitude of the entries in this matrix are sort of 1 for the block on the upper left, delta for the 2 diagonal blocks, and delta squared for the lower right block. Okay, so these are the order of magnitudes in the Malliavin matrix. And now we have to invert that. So how do you invert a matrix? Well, at least if you're not doing it numerically, you can try to use Cramer's rule. But if you're doing it numerically, this would be a bad idea. But here, Cramer's rule simply says, let's take 1 over the determinant times the matrix of cofactors. And so let's see what's in this matrix of cofactors. So the Malliavin matrix had terms of orders that are written here, 1, delta, delta, delta squared. So how do you get a cofactor? You sort of cross out a column and a row, and you take the determinant of what's left. So if I take an entry here and I look for the cofactor of that entry, I'm crossing out a column and a row that is comparatively large. And here in this example would give me delta square, so say in D equals 1, this actually works. If I take an entry down here and I look for the cofactor matrix, so I cross out a column and a row and I take the determinant of what is left, I've removed quantities that are comparatively small. So I'll be getting an entry that's larger than the cofactor of a term from this block. Okay, so you can sort of analyze the size of the cofactors, and you see here you have delta to the 2D as a cofactor for terms from the upper left block, and here a much larger quantity. So delta being small, delta to the power 2D minus 2 is larger than a quantity from up here. So again, you have the different orders of magnitudes in the 4 blocks for this matrix of cofactors. And now we want to use this. So remember I had this bound for this iteration of Skorokhod integrals in terms of norms of individual rows of this matrix times the column vector of Malliavin derivatives. And so what are the orders of magnitude of each of these factors? So of this factor, and so on. So I have the inverse of the matrix times the Malliavin derivative, this column vector. So this is, the inverse is 1 over the determinant times the matrix of cofactors times dz. So let me leave the determinant alone. This matrix of cofactors, we had written out the orders of magnitude here, and we had seen the order of magnitude of dz, also depending on whether you're in the first d coordinates or the last d. And so what happens if I take a row in the first d row, so a row from up here, I'm multiplying this row by this column. So delta to the 2d, delta to the 2d. So same order of magnitude is obtained from each contribution, this factor times 1, this factor times delta. I have an order of contribution of delta to the 2d. But if I take a row down here, I have delta to the 2d minus 1, and again delta to the 2d minus 1. So I have a different order of magnitude. So the blue factors are going to appear in these last d factors, and this expression will appear for the first d. So the determinant appears in every one of them. So it appears to the power minus 2d, minus 1 to the power 2d. And then this factor here is appearing in each of these d factors, and this factor here is appearing in the last d. Okay, so then you just check what exponent you're getting. You have 2d squared plus 2d squared, 4d squared minus d. Okay, so you have the determinant to the inverse of the determinant to the power 2d times this quantity. Okay, of course, hidden here is that I have to bound these coefficients of the inverse of the Malevin matrix in Sobolev norm, MP, for large M and P, but the order of magnitude is the correct one. Okay, so this is what I had obtained, the bound on the previous slide, the inverse of the determinant to the power 2d, and delta to this power. If we look at the Gaussian case, we can figure out what is the best possible estimate that we could expect to get here. And the best possible estimate for the inverse of the determinant is delta to the minus 2d. So minus 2d to the power 2d minus 4d squared exactly cancels this 4d squared. Okay, so the best possible estimate, if you can get this estimate for the inverse of the determinant, then you would be getting the best power here, delta to, so gamma equals d, delta to the power minus d. And then the other terms in brackets or this exponential factor haven't changed. Okay, so this is what we'd like to do, is have a good bound, the best possible bound on the inverse of the determinant, actually moments of the inverse of the determinant. So what have we actually been able to prove? Again, if we look at the four cases I've discussed, so the wave equation in spatial dimension 1, we have exactly the best possible result. Moments of the inverse of the determinant are bounded by delta to the power minus 2d. Delta is given by this expression. There's the same exponent in time and space for the wave equation in spatial dimension 1. The heat equation, delta to the minus 2d plus eta. So this is the eta that with extra eta that was appearing in the lower bound on hitting probabilities in the dimension of the capacity. And here also for the heat equation in spatial dimension bigger than 1, again, minus 2d plus eta. So close to optimal, but not exactly optimal. And then here is where the problem is occurring for the wave equation in spatial dimension larger than 1. 2d plus eta, that's still pretty good. But then this extra power, 2d minus over 2 minus beta. Okay, so this is sort of the extra quantity that's bothering us at the moment. The delta is the correct delta. Again, the same exponent in time and space for the wave equation. How do you estimate the inverse of the determinant? So remember, we have the Malevin matrix, and there were these orders of magnitudes in the four blocks. So this is a 2D by 2D matrix, but imagine that it's just a 2 by 2 matrix. And then its eigenvalues would be 1 plus delta square and 0. Okay, so 1 plus delta square would have this eigenvector, which is almost the vector 1, 0. And 0 would have this other eigenvector, minus delta 1. Okay, so there are sort of large eigenvalues of order 1 and a small eigenvalue of order 0. So this matrix, 2D by 2D matrix, will also have some large eigenvalues and some small eigenvalues. And the determinant is the product of the eigenvalues. It's a symmetric matrix. The inverse is the product of inverses. So it's important to distinguish between the large and the small eigenvalues. And so we're going to use this fact here that the eigenvector for the large eigenvalue is almost 1 and 0 to distinguish between large and small eigenvalues of this matrix gamma z. Okay, so gamma z is a random matrix with random entries. it's symmetric, it has an orthonormal basis of eigenvectors. And the determinant is the product of the eigenvalues, so it's written here. And so let's consider the subspace of R2D, where I put an arbitrary quantity in the first d coordinates and 0 in the last d coordinates. And so the point is that of these 2D eigenvectors, there will always be at least d whose projection on this subspace is comparatively large. So in the case of a 2 by 2 matrix, one of them had a large projection of length 1 onto this subspace. And here, alpha 0 might be smaller than 1, but it's strictly positive. And there are always at least d who have a projection on this subspace, which is fixed, it's not a random subspace, of length bigger than alpha 0. And I'll call these the large eigenvalues. And then there will be others, but at most d of them, which are small. And so the determinant is the product of the eigenvalues. So leave the large eigenvalues alone, or the determinant, the inverse of the determinant, product of inverses. Leave the large eigenvalues alone, because when you invert a quantity of order 1, it's essentially of order 1. And then you have the product of the small eigenvalues. So I just put the smallest one, and then it appears d times. And so this is the result that we have. The norm 2p of the smallest eigenvalue to the power minus d is bounded by delta to this power here. So d minus d times alpha. And again, this would be the best possible result in some sense if it was exactly alpha equals 2, close to optimal if I still had plus eta. And then there's this extra 2 over 2 minus beta, which is somehow ideally would not be present. And the large eigenvalues have a LP norm that's simply bounded by a constant. So these terms don't contribute, they just contribute a constant. And everything is coming from the smallest eigenvalue. But it was important to distinguish and figure out how many large and small eigenvalues there are. So where does this part A come from? So we're interested in taking the smallest eigenvalue, its inverse, and the LP norm. So how do you get an upper bound or an estimate on the LP norm? So you have to estimate this probability, which I'll call a small ball probability. So people doing Gaussian process study small balls. So what is the probability that this infimum is less than epsilon for epsilon small? And how does this, this is typically epsilon to some power. So you'd like an estimate of this kind. This expression, psi transpose times Malevin matrix times psi, gamma z, the Malevin matrix, is a matrix of inner products. So if you write this out explicitly, you get this expression, integral 0 to t dr, and then here you have the components of the vector psi appearing, and the derivative at time r and the spatial position of the components of the vector z. Here measured in a norm, which is the Hilbert space associated with the covariance of the noise. So you want the probability that the infimum of this integral is less than epsilon. And this is classically done using a method that was mentioned by Annie Millet in her talk this morning. So I think at the very end of her talk, she had an expression of this kind. And she did something which is completely classical, but the first time I saw this, I thought it was very strange to do that, which is you have this integral going all the way from 0 to t, and you simply remove most of the integral and take only the last part of it. And it's sort of odd because you want the probability that something is small, and you take something much, much smaller in some sense. But of course, for the heat equation and for the Cahn-Hilliard equation as she was considering, what you've removed in some sense is not significant. And so we did this for the wave equation. It's also what we did with Eulalia and Devar for the heat equation. And for the heat equation, it works fine, but for the wave equation, we did this, and it does not give the optimal result. So it gives the result that I've mentioned. Okay, because in the heat equation, you have a gt minus s, and most of the weight of that is occurring when s is close to t, so that this difference is not making you lose very much. But the kernel of the wave equation is very different. It's different in each dimension, 1, 2, or 3. and again in even higher dimensions. And you can do this, and we did this, and it gives the result that I mentioned. Well, this is sort of the beginning of a very long calculation for any of the cases I've mentioned, which gives us almost optimal result for the heat equation, but not for the wave equation. Okay? So it's sort of the very beginning of a long calculation that contains already the problem. And then the rest of the calculation contains a certain number of difficulties, but essentially you've done a bound that is much too crude here in the case of the wave equation, whereas for the heat equation it was fine. Okay, so I've just listed here the references for the papers that I've mentioned. So this first paper with Eulalia on the one-dimensional wave equation, and then the one-dimensional heat equation, first with additive noise, then with multiplicative noise. First paper with Marta Sanz for wave equations, mainly the linear equation, and then this result on the heat equation, higher spatial dimensions, and this paper that we worked on mostly here and finally finished for systems of wave equations. So thank you for your attention.
Time for question. The application to compute Hausdorff's dimension of graph and level sets, these gaps count. The Hausdorff dimension is not strict.
So obviously if you don't have the right estimate on the hitting probabilities, then you will not get the correct estimates. You'll get upper and lower bounds, but you won't say the level set has this dimension, for example. Whereas if you have the correct bound, say in the case of the heat equation, then you'll get the correct Hausdorff dimension.
So the problem is not solved by other methods. So these are
No. It's sort of building on using the hitting probabilities and then doing some sort of general argument.
state of the art, also for the outer dimension.
Yes.
No question. We thank you.